Hello and namaste everyone, welcome to my channel SigmaX. Today we are learning about LCR circuit in series combination. If you haven't watched my previous video on LCR circuit, then I strongly recommend you to check it out first. You can watch it by clicking here or following the link in the description below. Also, in my next video, I will teach you how to solve any physics numerical problems. If you don't want to miss that video, then hit that subscribe button and press the bell icon so you can get notification when I upload it. Now, let's start our journey by considering a pure resistor of resistance R, a pure inductor of inductance L, and an ideal capacitor of capacitance C connected in series to a source of alternating EMF as shown in this figure. Since resistor, inductor, and capacitor are in series combination, the amplitude and phase of current at any instant of time through these three elements will be same. However, voltage across each element has different phase relationship with the current and they reach their maximum value at different times. If E be the value of applied alternating EMF to LCR circuit, VR be the potential difference across resistor, VL be the potential difference across inductor, and VC be the potential difference across capacitor at any instant of time t, then it is crucial to note that the maximum amplitude of AC voltage source E0 is not equal to the sum of maximum voltage amplitudes across the three circuit elements. That is, E0 is not equals to VR0 plus VL0 plus VC0. This is due to the fact that the voltages are not in phase with one another. Therefore, to find the relation between maximum amplitude of source and potential differences, we should first know the nature of voltage amplitudes and draw the phasor diagram. As we know that in resistor, voltage and current are in phase. Therefore, in phasor diagram, maximum voltage across resistor, that is VR0, is represented by OA in the direction of reference vector current I0. Similarly, in inductor, voltage leads the current by a phase angle of 90 degree. Therefore, in phasor diagram, maximum voltage across inductor, that is VL0, is represented by OB in the direction perpendicular to I0. Also, in capacitor, voltage lags behind the current by a phase angle of 90 degree. Therefore, in phasor diagram, maximum voltage across capacitor, that is VC0, is represented by OC in the direction perpendicular to I0. Now, from this phasor diagram, we can say that the vector sum of maximum voltages across resistor, inductor, and capacitor will give us the maximum amplitude of AC voltage source E0. So, if OR represents the maximum amplitude of AC voltage source E0, then we can write magnitude of E0 equals to magnitude of VR0 plus VL0 plus VC0. As we can see that VL0 and VC0 are in opposite phase, so their resultant will be VL0 minus VC0, taking VL0 is greater than VC0. Let the resultant of VL0 and VC0 be represented by OD, which is perpendicular to OA. Hence, using the parallelogram law of vector addition, we can write the magnitude of resultant OR equals to under root OA square plus OD square, or E0 equals to under root VR0 square plus VL0 minus VC0 whole square. Since VR0 equals to I0 times R, VL0 equals to I0 times XL, and VC0 equals to I0 times XC, we get E0 equals to I0 times under root R square plus XL minus XC whole square, or E0 divided by I0 equals to under root R square plus XL minus XC whole square. Let it be equation 1. Comparing above equation with Ohm's law equation, that is voltage divided by current equals to resistance, we find that under root R square plus XL minus XC whole square has the dimension of resistance. Therefore, it is called impedance of LCR circuit and is represented by Z. Hence, impedance is the total opposition offered by LCR circuit to alternating current. Also, the reciprocal of impedance of a circuit is called admittance and is denoted by A. That is, admittance A equals to 1 divided by Z. Note that impedance is measured in ohm. Therefore, the unit of admittance is per ohm or mho or Siemens. Also, in equation 1, since E0 and I0 are in ratio, we can write RMS value of E divided by RMS value of I equals to E0 divided by I0 or under root R square plus XL minus XC whole square. Now, let theta be the phase angle between E0 and I0. Then, from right angle triangle OAR, we have tan theta equals to AR divided by OA, which gives us VL0 minus VC0 divided by VR0, which is equal to XL minus XC divided by R. Hence, theta equals to tan inverse XL minus XC divided by R, or tan inverse L omega minus 1 divided by C omega whole divided by R. Now, let's learn some special cases in LCR circuit. Case number 1. When inductive reactance is equal to capacitive reactance. If inductive reactance is equal to capacitive reactance, then impedance Z will have the minimum value equal to resistance R. Hence, the current in the circuit will be maximum and therefore the circuit attains electrical resonance. Also, tan theta equals to 0, that means theta equals to 0 degree. Therefore, the voltage and current will be in same phase. Thus, the AC circuit will be non-inductive. Case number 2. When inductive reactance is greater than capacitive reactance. If inductive reactance is greater than capacitive reactance, then tan theta becomes positive, so theta becomes positive. Hence, voltage leads the current by the phase angle theta and therefore the AC circuit is called inductor-dominated circuit. Case number 3. When capacitive reactance is greater than inductive reactance. If capacitive reactance is greater than inductive reactance, then tan theta becomes negative, so theta becomes negative. Hence, voltage lags behind the current by the phase angle theta and therefore the AC circuit is called capacitor-dominated circuit. Finally, we have come to the end of this video. I hope by watching this tutorial, all of you have understood much more about LCR circuit. Thank you so much for watching. If you like this video, then please don't forget to like, comment, share and subscribe to my channel. And also don't forget to press the bell icon so you can get notification when I upload a new video. I will see you guys in my next video. Till then, bye bye.